Hello students, welcome to Saraswat classes, and today we are discussing retrosynthesis of esters. So we will begin the lecture by saying that the retrosynthesis of ester target molecules typically begins with a disconnection of CO bond. Now, this CO bond, as we have discussed, forms when there is a nucleophilic attack by the oxygen and it is reacting with the electrophilic carbon, that is either a acyl or a carboxylic derivative such as the acid chloride. So here in our retrosynthetic pathway, say number 1, so this is our given ester. So we wish to disconnect at the CO bond, as I have said, which means that this particular carbon, that is the carbonyl carbon, as the reaction was happening, was the electrophilic center, that is the carbonyl carbon of a acid chloride, and this oxygen over here was the nucleophile. So on disconnection, the synthons that are formed can be written as follows, where we will assign this to be the electrophilic carbon and this one will be our nucleophile, and hence we will say the synthetic equivalents for these synthons. We will write the acid chloride, which has the electrophilic center, this one, and our nucleophile over here is the alcohol. So reaction between these two molecules, leads to the formation of the ester. One information about this reaction is that this is suitable for any R prime group. That means methyl primary, secondary or tertiary. However, there is another possibility in which the carboxylate ion can act as a nucleophile towards a alkyl halide. So in those cases, we have to think the disconnection happens over here. And as before, we will say this particular oxygen was the nucleophile and this carbon was the electrophile, that is R prime X. So on disconnection, the synthons produced out here is the carboxylate, which is our nucleophile, and R prime plus will be our electrophile, for which the synthetic equivalent will be the alkyl halide having the electrophilic center, And the key point about this reaction is that it is suitable for unhindered R prime X only. Now it is worthwhile to mention over here that if the alkoxy group is bulky, or let's say it is highly substituted, or is a phenoxide derivative, then the process that can be used to make these kind of esters will not involve any SN2 type reaction as we have been using here, okay? Because typically out here what we will say is that this particular will make a SN2 attack on this, that will go away and the ester is formed, okay? So we'll not use the second disconnection approach, in which this is the second disconnection approach, that is what we are not going to use over here. But out here these type of esters should be prepared by acyl group substitution or by peroxy acid oxidation from the corresponding ketone. That means to make esters of these kind, we will start with and we will use MCPBA, okay, or else we will react the acid chloride with the sodium phenoxide and synthesize the desired product. That is our target molecule. Okay. Now in the next section we will be discussing the retrosynthesis of lactones. Now what are lactones? Lactones are basically cyclic esters and they can be prepared by oxidation or possibly by a cyclization reaction such as an intramolecular Fischer esterification this can be used if the lactone is 5 or 6 membered ring, also called gamma and delta lactones respectively. So suppose this is our lactone. So if we go back and try to find out what should be our starting material, then we can start from a cyclobutanone, and one can do or use the peroxy acid oxidation procedure to make the gamma lactone. Or also one can think of the intramolecular Fischer esterification, okay, over here to make the gamma lactone. Similarly, delta lactones can be made, one can think using cyclopentanone, or one can use Fischer esterification and make the delta lactone. Now how is the naming happening? If this is the alpha, this is our beta, this is gamma, this is alpha, this is beta, gamma, and this is delta. Okay. So now we have discussed the retrosynthesis of lactones. In the next